Swayam Prabha. Digital India. Educated India.
So, the next result says that again we will start with a directed acyclic graph, because we will base our argument on this previous results. So, with vertex set being labeled like 1 to n, and let B be the anti-adjacency matrix of G. So, now let us look at, previously we were looking at determinant, eigenvalues and all, right. We connected our adjacency matrix with the characteristic polynomial, right, a minus lambda I we took, right. Now, we are going to do the reverse, so kind of a reverse. So, we can now look at determinant of some vector x into B plus I. Say suppose this is, you will obviously get a polynomial, right. If you take a determinant of this, you get a polynomial in x, right. So, let us give a representation for this as C I x power I, where I is equal to 1 to n. Then in fact, it is a polynomial of degree n, means we have n plus 1 coefficient. So, I should also include that. So, I equal to 0 to n, right, constant term is there, plus n degrees n powers of x will be there. So, then the C naught, the constant term, is going to be equal to 1, and you look at the coefficient C I gives you the value that I was telling you. C I equals the number of directed paths of I vertices, any I subset we could look at in G. So, C naught equal to 1 means what? If you look at this characteristic polynomial, this x b plus I, okay. So, it is also kind of a characteristic polynomial, right. If you just expand this B as j minus I, j minus A, okay, then you are like kind of looking at the what do we call eigenvalue equation, right, characteristic equation we are looking at. So, in that sense you can see that the C naught is going to be nothing but determinant of this matrix B. Okay. So, we have already seen that if there is an Hamiltonian path, determinant will be 1, otherwise 0. So, C naught equal to 1 implies that there exists a Hamiltonian path, and there is only one Hamiltonian path in the graph. There cannot be two paths, right. Can there be two Hamiltonian paths in an acyclic graph? In an acyclic graph, right. If there were two paths, then obviously I will form a cycle out of both the paths, right. So, since we are talking about acyclic graph, there is only one Hamiltonian path if it exists, okay. And in this case we can easily count those vertices, okay. Okay. And the remaining, similarly C I is going to be nothing but you look at any I by I submatrix, right. So, that submatrix again you can say that you will be counting all possible I by I submatrix. Determinant of that submatrix will be 1 only if there is a directed path in that I matrix on that on those I vertices, right, otherwise it will become 0 again. So, just a generalization of these results, you can immediately say that the count holds very good for us, right. Okay. So, I have said so much of things, now let us go back and see for this example, okay, can I justify my result whatever I have stated for this example here. Okay. So, obviously I know this time I will not ask you to solve for my polynomial. So, for that B matrix, let us see what determinant of xb plus I is going to be equal to. Okay. So, I will give you the polynomial, you can verify it. Okay, so, it is going to be x power 5 plus 4 x power 4 plus 7 x cube plus 7 x square plus 5 x plus 1. Okay. You can cross check this. This b is for the graph that we had taken, okay, b for the example considered, right. So, what does this tell you? So, each of this term tells you about your CIs, right. So, if I try to list down based on my I value and the directed paths, can you guys do that? Say suppose I equal to 5, or should I go from the reverse direction? Let me just go back to this example. So, this example is what we are talking about. So, I think I have to copy this over here, or I will redraw it, it is not a problem. So, we are talking about this graph with directions. So, 1 to 2, 4 to 1, 4 to 5, right. So, now can you give me directed paths that will fit into all these categories? So, I expect there is one directed path or a Hamiltonian path on 5 vertices, right. So, it is going to be 4, 1, 2, 5, 3, right. I am just giving the path, you can just assume that is the direction, it is direction of flow. What about 4? So, we should be looking for 4 paths of length 4, I mean on 4 vertices, right, 4 directed paths. 1, 2, 5, 3, 4, 1, 2, 3, 2, 5, 3. It should not form, I mean obviously it will not form cycle, so it is a cyclic graph. Yes, one more, 4, 1, 2, 5, right. So, there are 4 directed paths. If you search for it, you will not get any more out of this, right. Now, for 3, on 3 vertices, 1, 2, 3, 1, 2, 5, 2, 5, 3, 4, 2, 5, 4, 1, 2, 4, 5, 3. Anything else? Four, 2, 3, right? Yeah, 4, 2, 3, yes. 1, 2, 3, 7 has come in. So, we have 7 paths and there is no more, right. You can exhaustively search here and see that it is satisfied. Now, on 2 vertices, there are 7 edges. So, only those things will have to form. So, you can immediately write 1, 2, 2, 3, 2, 5, 5, 3, 4, 1, 4, 2, 4, 5, right. And what about on one vertex? It is just singleton vertex, right. So, you can just pull that out. So, 1, 2, 3, 4, 5. I mean when we say on one vertex, there is no path, but there is a vertex there, right. Okay. So, this kind of matches up with the theorem. Okay. Again, proof is very simple, you just need to look at the determinant, expand it, and you will be able to give this argument based on the paths. Okay. So, as I said, yes, we have taken half an hour exactly on this. So, for the next topic, so now this is about anti-adjacency and I have done it for a cyclic graph. Okay. I am just giving you a flavor of each matrix and how it behaves. So, there are many more results for anti-adjacency matrix and other graph classes also. You can try to look for special matrices when you will get, and can you characterize your graph based on the matrix structure. right. So, all these kind of studies can be done here, and there can also be like very well written algorithms to compute all of these things, right. Yeah, but it will not have, right, that is what we are talking about here, right. Ci equals the number of directed paths of I vertices in G, right. If so, that means what I am talking about C5 x power 5. So, C5 in this case it is directed acyclic graph, good, but this result will not hold, because here we rely totally on the determinant being equal to 1 or 0, right, because this structure is very special. Your lower triangular matrix is all ones. So, because of that you know determinant is either 1 or 0. If it is not the case, your determinant could be anything else also, any value, it could be any integer, not also possible, right, even rational number, any real number. Right. So, in that case we have to make a detailed study. There are results, but that needs a little bit of lengthy proof that you need to think about. How do you interpret the coefficient? Can you interpret it as directed paths? But in this case we could do it because we know the structure. So, if there is no question, then we will go back to again adjacency matrix, but for the class of trees. So, what can we say about the determinant of the adjacency matrix in the case of a tree? So, we are talking about the adjacency spectrum and determinant. So, already we have seen for directed trees, right, acyclic graph we have seen with anti-adjacency matrix. So, now I am going into adjacency matrix of trees, okay. Whether directed or undirected we can think of it. So, what can we say about the determinant of this? Say if A is going to be the adjacency matrix of T, A of T, I will just denote it. So, there is a simple terminology. If your determinant of this matrix is 0, we know it is singular, right. So, then we call our tree also a singular tree. If determinant is non-zero, that is if my matrix is non-singular, then I call my tree also a non-singular tree, okay. So, determinant is not equal to 0 implies my tree, I just call T is non-singular, because singular tree sometimes does not give us big results. With non-singular trees we can do a lot of effective things, okay. So, why do we want to call this as a non-singular tree, and how do we characterize a non-singular tree? For which trees will my determinant be non-zero? So, to get this we have to go back to the definition of our adjacency matrix in terms of the elementary subgraphs that we have seen, right. So, we know determinant of A is nothing but sigma minus 1 power n minus C1 of h minus C of h into 2 power C of h, right, where C is number of cycles and C1 is number of edges in a spanning elementary subgraph, right. So, where h is a spanning elementary subgraph of G, right. This we know. So, from here can you say something about the tree? Obviously, we know C is 0, C of h is 0 because there is no cycle in the tree. So, C of h is 0, so that is ruled out, 2 power 0 is 1, and so we have to now worry about n minus C1 of h, right. So, when will this quantity exist, or when does a elementary subgraph exist in simple term? So, what is my elementary subgraph now? Since there is no cycles, it has to be only collection of edges, right. So, when will we have a collection of edges? Even number of vertices, right, and even if we have even number of vertices, can I have an elementary subgraph of edges? How should my elementary subgraph look like? Obviously, if I have, so this is on even number of vertices, right, 1, 2, 3, 4, but how many elementary subgraph I can get out of here? I mean spanning. There is no spanning elementary subgraph here, right. So, what is that? There is an elementary subgraph, I can look at, I have to get used to it. So, I can get an elementary subgraph, say 1 2 is an edge, it is an elementary subgraph, 2 3, 2 4, they are all elementary subgraph, but do they span my graph? Collection of components, right? We are talking about spanning subgraph here. So, what should be there in that case? Yes, a perfect matching, right? If we have a perfect matching, then we can say that our T is non-singular, right? So, this is the next result. So, let T be a tree with n vertices again. So, I am just giving you proper statements labeled 1 to n. Then the adjacency matrix of tree A of t is non-singular if and only if there exists a perfect matching. Just from the definition you can see immediately this result will hold, right. So, one way we can immediately see from this, right, for an elementary subgraph to exist, first of all tree must have a perfect matching. What about the other way around? If my tree has a perfect matching, then how do I show that determinant is non-zero, or I mean the tree is non-singular? So, again we will go back to this only, we are going to just beat around this bush only. So, how many such elementary spanning subgraphs are possible? If I tell you that a tree has a perfect matching, only one, right? If there cannot be two perfect matchings, right. So, if there is a unique perfect matching, then to this sum the contribution is going to be coming only from that one elementary subgraph, right, spanning elementary subgraph. So, that would be just nothing but the number of vertices, right, it is going to be n minus n by 2 you will get. So, this quantity is going to become a non-zero quantity. Right. So, with only one term that will be existing and my C1 of h, the number of edges in my graph would be n by 2, right. So, just this quantity would become a proper non-zero entity. So, therefore, I can conclude determinant is non-zero. Okay. So, that is again a simple proof for the if and only if part, right. Okay. So, this is about adjacency matrix and non-singular trees. In this direction there are, again I am just giving you a flavor of each and every one of these results. Okay. If you are interested, you should go back and read all these things. You can also think of computerizing these results, because each of this proof is a kind of an algorithm. If this holds, then you go to the next and so on, right. You can try to compute the number of trees, number of spanning trees, all those things whatever we have been seeing. Okay. For trees, at least trees, there are lots of results, and for also regular graphs and strongly regular graphs, all those things, right. So, how much time I have? Okay, I have another 15 minutes, right. Yeah. Okay. So, next, before I go into the next result, I will not give the proof, but we will discuss about the results. Let us now consider a Laplacian matrix, okay. And if T is a tree, then what can I say about its eigenvalues and its multiplicities and the behavior of those eigenvalues. Okay. So, again let us start with, let T be a tree on n vertices. So, this is kind of our standard statement for today. With, let us talk about the Laplacian matrix. Okay, let me call it as L of t. Okay. So, if I want to look at the eigenvalues of this Laplacian matrix, okay, Then one interesting result what it said is like if I have an integer eigenvalue for Laplacian, okay, then that integer should be a divisor of n. Okay, if there is an integer eigenvalue, then it has to divide n. Okay. So, if lambda is an eigenvalue of L of t, say let us also look at the corresponding eigenvector. We will also declare something about this with the corresponding eigenvector of x. Then the first statement is that if lambda is an integer eigenvalue, let me also put that, is an integer eigenvalue, then lambda divides n. Okay, if it is integer, there can be non-integer real values also. So, we are only talking about integers, and the multiplicity of this eigenvalue, okay, it is going to be equal to 1. So, it cannot occur in pairs or triple, it cannot repeat itself, right. And further we can also say that every component of the corresponding eigenvector x, okay, it is going to be non-zero. Your component will have only non-zero entries in that. Okay. So, no coordinate of x is 0. So, this is something that looks very interesting to see, like if you have an integer, then these things are all kind of it follows along with it. Okay. The proof is simple, you just need to go into the representation of the determinant, expand it, and you can see it from there why this will hold. Okay. So, another one about Laplacian eigenvalues for trees. Okay. Not only for trees, I can say in general also. We were talking about algebraic connectivity yesterday, right. What about lambda being equal to 1 as an eigenvalue? When can it occur? Okay. Or there is also another direction of study where you can count the number of eigenvalues and describe the structure. Okay. Based on the eigenvalues where it lies, you can talk about the connectivity and other things about the network. So, we know that if my algebraic connectivity is 0, then we know its graph is disconnected, right. This is known. So, what about if it is bigger than 0, but how much big? How much big this could go on? So, there is a study about the algebraic connectivity lying in this region 0 to 1 or 1 to infinity. I am just putting it in a rough term. As n increases, we can talk about this also, 1 to n, right. And what about 1 itself being an eigenvalue? Okay. So, now when I go into 1 itself being an eigenvalue, I am not talking about algebraic connectivity, okay, because 1 need not be the second smallest eigenvalue. There are possibilities where your eigenvalues can be like 0.002, I mean 0.238, like this, right. Like in one case where we have at least seen, we have a 1 minus cos pi over n for path graph, right. So, for that if you see, the value would be much less than 1, right. So, there is also a study about 1 being an eigenvalue and for which graphs it is possible that 1 could be an eigenvalue. Right. So, again trees comes into picture here. If 1 is an eigenvalue, okay, then the graph has to be a tree, okay. And we can also talk about the multiplicity of this 1 as an eigenvalue in terms of the structure. Okay. So, this is the next one that I want to talk about. So, again let me start with, let T be a tree with L of t. So, we are now with Laplacian. So, with L of t being given to us. Okay. If lambda is an eigenvalue of t, of L of t of course, when I am talking about t of L of t, and if my tree has say p pendant vertex. So, what is a pendant vertex? Degree 1 vertex, right, all the degree 1 vertex. So, if there are p pendant vertex, then the multiplicity of lambda, the occurrence of lambda, okay, depends on this p, and it can never exceed p minus 1. Okay. So, m of lambda, so this is the notation that we give for multiplicity. Okay. So, multiplicity of lambda is going to be less than or equal to p minus 1. So, number of pendant vertex, and actually in the next result we will be talking about number of pendant vertex and its adjacent vertices. We call it quasi pendant vertex, that is all those vertices which are adjacent to degree 1 vertex. Okay. So, these two have a big role to play. So, how do we even prove this is, you just look at all those vertices and the corresponding eigenvalues. The multiplicity cannot exceed this in the determinant expansion. Okay. So, the degree 1 vertex play a big role as far as trees are concerned at least. So, this is one interesting result that I want to tell, and another one is in same line, in similar line, if suppose p is the number of pendant vertex and q is the number of quasi pendant vertex. So, by quasi pendant we just mean that all those vertices which are adjacent to degree 1. Okay. So, this is a quasi pendant. Then we can say, talk about one occurring as an eigenvalue in this case, and say that the multiplicity of the eigenvalue 1 in this tree, for this tree is nothing but, we know this, the upper bound is given by the previous result p minus 1, and the lower bound is coming from the number of pendant vertices and number of quasi pendant vertex, right. So, you can obviously see that if there are p pendant vertices, there are at most p quasi pendant vertices, right. For every vertex you can have a kind of a quasi pendant which is connected and so on, right. So, the q value is going to be less than or equal to p. So, this p minus q is a well defined non negative quantity. Okay. So, in the case if p is equal to q, you can simply see that the multiplicity could be 0 also. So, that means what, 1 does not occur as an eigenvalue, that is also a possibility. So, these are some results which I just wanted to share about Laplacian eigenvalues. Okay. And I am not giving the proofs here, but if you are interested you can just go look into it. The proofs are quite easy to follow, you can just read through them and you can find the proofs. Okay. Because it is kind of repetitive argument, again and again I have to say the same thing, look at the determinant, expand it this way, that way. So, I will leave that part to you as an exercise. You can take the books, I have given already the reference books also, right, in this direction. So, if you are interested you can pursue further in this, and I should also tell some of you here, large number of results in this direction on this algebraic graph theory are proposed or solved by computer scientists. Okay. So, do not think that this is a mathematician's job and I do not have to know all these things. Okay. This result obviously, this kind of study was triggered by computer scientists and they needed to solve it, okay, to study further about networks and other things. So, it is relevant for you, so believe in that, and try to learn it more. Okay.